Hi, so this is Unit 4, Class 2, where we're going to be looking at Riemann sums. So the first thing I want to do is just kind of look at some of the notation. Um, so you can see the notation here. When you did the homework, you saw that there were the three different kinds. N is the number of rectangles that you're going to use. And then the height can be determined by either the right bound, the left bound, or the midpoint. And so you'll always be told which approximation you're going to use. So R sub n is going to tell you use the right-handed with how many rectangles. L sub n, the left-handed. Change in x is also something you're going to see, and that is the width of each of the rectangles. Now, a lot of the time, if you're calculating this given an equation, it's going to be the width is going to be the same for every single rectangle. If you're given, oops, I forgot the L. If you're given um, a table of values to approximate the area underneath the curve, then perhaps change in x is not going to be the same, but it is b minus a over n, where b is the upper bound of your interval and a is the lower bound of your interval. So this is just some notation that you're going to be seeing. So I wanted to get that out of the way now. All right, so I just want to again look. I know you guys looked at a demonstration in Desmos. This is one in Wolfram demonstrations. So here you can see you have all those rectangles, and this one, for each of the rectangles, you're using the left-hand side to determine the height. So the rectangle goes up to the curve, and then where that left side of the box hits the curve is going to be the height. So this is the L of 6. The left-hand approximation was 6 rectangles. Now I go to the right approximation. Here, your change in x is the width of the rectangle, but now for every box, the right-hand side of the rectangle determines the height of that rectangle. So this is the right-hand approximation for 6 rectangles. Now you can kind of see here you have each of the rectangles is a little bit over the curve. So it's a little bit of an over approximation. But remember, these are approximations. Now the last one that you should have seen is the midpoint approximation. So that is literally using the middle of each of those rectangles to determine the height. And that's m of 6. And you can kind of see here you have a little bit over and a little bit under. It's still an approximation. Those two pieces are not the same, though, so you have to keep that in mind. Okay, so we're going to look at the homework that you guys did, and hopefully you had some type of visual of what this would look like from the Desmos demonstration. Okay, but now we're really going to be focusing as well on the correct notation and all of that. I mean, the general idea, don't forget, is that you're approximating the area underneath a curve using rectangles. And the area of a rectangle is base times height. Okay, so the first one, I'm going to do the left approximation. So I know it goes from 2 to 4, so that's what I'm going to write first. And then I know I need 4 rectangles, so I'm just going to break it up into 4. Now you'll see this curve is, it does look quite similar to the natural log of x actually, but it's very much a visual for me. It is arbitrary. I just kind of draw the curve so I can get a visual for what I'm finding. So now I can find the width of each rectangle. I know I need the left bound, and I can find the width of each rectangle by saying b minus a over n, where your b is 4 and your a is 2. That's the interval that you're given. So 4 minus 2 over 4, because n is the number of rectangles, and they said 4 rectangles. So I get a change in x of 1/2. That means the width of each of my rectangles is going to be 1/2. So that's going to be 1/2. All of these will be 1/2. All right, so now I'm going to take a look at my first rectangle. I have to use that left bound as my height. So there's my first one. It has a width of 1/2. Okay, my second one, my third one, my fourth one. So notice the height of each rectangle, I go up to the curve and over to the right so that the curve is determining the height on the left-hand side of my rectangle. So now I need to look at the height. So I know the width is 1/2 and the area is width times height. So the height of this first one is going to be the height of the curve at 2, which I can display as f of 2. It's the function at 2. And my next height would be f of 2.5, right? I know it's going to be 2.5 because the first one's 2, and then I'm adding 2.5. And then I go another half over, which is my change in x, and I get f of 3. And then my last rectangle will have a height of f of 3.5. So now I can find the area underneath the curve, well, an approximation for the area underneath the curve. And I'm going to use my left approximation, so that's the L of 4. And so the first rectangle is going to be 1/2 times f of 2, right? Base times height. And then all the other rectangles are going to go from that. So you'll see 1/2 f of 2 plus 1/2 f of 2.5, that's the area of the second one, plus 1/2 f of 3, which is the area of the third, and then 1/2 f of 3.5, which is the area of the fourth rectangle. Now, because 0.5 is a common factor there, I can just take that out, and I could say 0.5 times f of 2 plus f of 2.5 plus f of 3 plus f of 3.5. This is something that you need to show within your work. It is something that they will be looking for in the AP exam, and it is something that I will be looking for as well. Okay, we don't just want to write the numbers because there's no indication then of where those numbers came from. You writing this line is going to tell me where those numbers came from. Now I'm going to find this number using the calculator. All right, so first I'm going to show on the 83, 84 how to do this. So the first thing I do is I put in the natural log of x into y equals. Now I can go over to my main screen and I'm going to use that vars button. So I'm going to do 0.5 parentheses, and now I'm going to do vars, y1, because that's where I put the natural log of x, parentheses 2. Right? So remember, the calculator is going to put in that value of 2 into the function and then calculate it for us. So I'm going to put in that entire line that I just wrote on the previous slide. And just so everybody knows, I will be showing this on the Inspire as well with the right and the midpoint approximation. But this is the most efficient way to do it using the vars button. And I know with the natural log of x, you could argue about whether it's easier just to put in, the natural log of 3 plus the natural log of 2, but this is a really important method for more difficult equations. Okay, so now I'm going to find my right approximation. And my right approximation is going to be starting the same way, right? I have 2 to 4. I'm still going to have the 4 rectangles, and the change in x doesn't change as well. That is still 1/2. Okay, but now my rectangles are going to be, the height is going to be determined by the right-hand side of the rectangle. So here I've drawn the approximation for each of the rectangles. Now this means the height is also going to be different for each of them. So For this one, you're going to have f of 4. For this first one, it's no longer going to be f of 2, but f of 2.5, and then f of 3, and then f of 3.5. So you can notice while the left one was using all the heights except the last, the right is going to use all the heights except the first. So now my right approximation with 4 rectangles is going to be equal to, again, I'm looking at the area of each of the rectangles. So the first rectangle will have an area of a half times f of 2.5, and then the second will have a half times f of 3, a half times f of 3.5, a half times f of 4. And again, I could take out that 0.5. Now I'm going to use my calculator to then find that. Okay. Before I do that, I am just going to do my midpoint approximation as well. So my midpoint approximation is very similar. It starts out the same way. You have the 2 to 4. You still have the 4 rectangles. Okay. But now you have to remember that if the width of each of those rectangles is a half and it has to go in the midpoint, then from the bound to the midpoint is going to be a quarter. And then from each midpoint to the next midpoint will be a half. Okay, so my first rectangle you could see there, so that height is being determined by the midpoint of each one. So the height now is going to be determined by the x-coordinate of not 2.5 or 2, but 2.25. So 2.25, 2.75, 3.25. So again, I get the 2.25, and then what I do is just add a half to each one to get to the next midpoint. Okay. So M of 4 denotes that we're using a midpoint approximation with 4 rectangles. And now the idea is still the same. The width of each rectangle is still a half. And then you have f of 2.25, f of 2.75, etc. Again, I could take out that 0.5. This step is extremely important. So now I'm going to use my calculator to show you how to do this very quickly. But remember, this line, while your final answer is of course important, this line is also necessary within your work. Okay, so now I'm going to do those two calculations on the Inspire. So on my graph, I'm going to put in the natural log of x. So there is my function. And now I'm going to go over to my main screen, my scratch pad. So you could just click on the side there or go to home and then, and then the scratch pad. So now I'm going to do the same type of thing I did before. I'm going to use that vars button. Now the vars button here though is you just hit that vars that's above the 9 and then you can plug in f of 2.5. So the same type of process as with the 83, 84. It's a little bit different. That's why I wanted to show it. But this is going to be the calculation for my right hand approximation, and I'll also do the one for my midpoint. So you can kind of already see the process is a little bit quicker for the Inspire, but it's still the same. Again, this is using that vars button is going to be your most efficient method, particularly when you have equations that are quite long or very detailed. So there was the approximation for the right, and now I'm going to do the midpoint. Again, the same thing. You really want to watch your parentheses where you're putting them in, right? So that 0.5 can multiply by the entire thing, so I do include parentheses around all of those values of f that I'm summing together. So I put those in. Okay. Remember, a good thing to remember, if you have 4 rectangles, you should be having 4 heights here. So I have the 2.25, 2.75, 3.125, and then I should have one more, right? So if you have 5 there and you're only supposed to have 4 rectangles, you know something went wrong. Okay, but here is then my approximation for the midpoint.